Hello, so today we are going to be talking about non-steady state mass flows. So we are going to begin by looking at this tank, which has a stirrer in it, and it is filled to some level. So having a stirrer in this tank means that our tank is completely stirred, so the product at the bottom and at the top is exactly the same. It's completely stirred through. So here we are going to have a flow rate going in, so that's going to be Q in. And we are also going to have a flow rate coming out, so that is Q out. So then if we're looking at this tank, we are going to be able to see that we are going to have a cross-sectional area everywhere throughout that tank that is going to be constant, so that we are going to call that A. And then we are also going to have a height over here to the top of the water, and we're going to call that H. So now if we look at this, the temperature that is going to be inside our tank is going to be our temperature initial. And we are also going to have a temperature going in and a temperature coming out. So if we look at all these values across the top here that I wrote out beforehand, these are from our problem. So our temperature initial is going to be 300 Kelvin. Our temperature in is going to be 320 Kelvin. Our temperature out, we do not know yet. And then our Q in is 1 meter cubed per second. Our Q out is going to be equal to what we're calling alpha, which is 0.4. So it's going to be alpha times the square root of H. Our area is going to be 1 meter squared, and our height is going to be 1 meter. Alright, so now we are going to find an equation for our height. So to find our equation for height, we are actually going to look at the mass of our system. So we are going to start out by looking at the change in mass of our entire system, which that would be equal to the change of the mass going in minus the change in the mass going out. So now we don't know the masses of our system, but we can find each mass using the values that we do know. So our mass of our system is going to be the change in the density. So that's the density of our water inside of our tank times the area times the height. So the area times the height is our volume of our tank. Now this is all going to be with respect to time because our height is going to change with respect to time. Now, on the other side, we are going to have the density times Q in for our mass in minus our mass out, which is going to be density times alpha times the square root of H, because we said earlier that our Q out is equal to alpha times the square root of our H. So now we are going to divide to the other side by density to get rid of all the densities here. So we are going to have the change in, we are also going to pull this area out because our area is not going to change with time. So we are going to have area times the change in height over the change in time is equal to Q in minus alpha times the square root of H. So now we are going to divide A onto our other side. So we are going to get the change in height over the change in time is equal to Q in minus alpha times the square root of H over the area. So this is our equation for height. Alright, so now we are going to find an equation for the temperature in our system. So if we begin to look at this, we can find that the temperature is equal to the change of mass times the energy of the internal system plus the kinetic energy plus the potential energy. Now this would be set equal to the enthalpy plus kinetic plus potential going into our system times the change in mass going into our system minus the enthalpy plus kinetic plus potential going out times the change in mass going out. So now if we're to look at this, we can see that our kinetic and potential energies here are going to be so little that they are not going to change anything. So we can just ignore all of these. So we are going to have the change in mass times the internal energy of our system is equal to the enthalpy going in times the change in mass going in minus the enthalpy going out times the change in mass going out. So now if we can see that this equation here looks a lot like our equation that we used up in our height to find our height. So we can now look at this as the change in the density times area times height times the energy of the system over the change in time. So this is with respect to time because our H and U are going to be changing. And this is going to be equal to the enthalpy going in times the density times the QN minus the enthalpy going out times the density times alpha times the square root of the height. So now we're going to do the same exact thing that we did up there, and we are going to pull the height and the density out of this side of the equation. So we are going to get we're going to pull the area and the density out of this side of the equation. So we are going to get area is equal to the change in height times the energy of the system divided by the change in time. And this is going to be equal to enthalpy in times Qn minus enthalpy out times alpha times the square root of H. So now we are a little bit stuck with switching around this equation, but since our tank is full of a liquid, we can have the change in our enthalpy would be equal to the specific heat times the change in the temperature. And then we would have the change of the energy of our system is equal to the heat capacity times the change of temperature. So now if we were to derive this equation, we could see, or no, we're not deriving. If we can see that we have the change in our energy, so if we have the energy at a time t minus the energy at a reference time, this would be equal to our CV times the temperature at a specific time minus the temperature at a reference time. And now if we can see that these would end up actually being CP would be equal to CV. So now if we go back down here, we can now use this and we can plug this back in. So we are going to have A times DH times CV times the temperature minus a reference temperature divided by the change in time is equal to CP times T minus a reference time. So we didn't actually write this one out, but we can see that if we do the exact same thing that we did down here for the energy equation, we can do that for our enthalpy equation too and use it in this way. So this will be times Qn minus CP times T minus a reference temperature times our Q out, but that is going to be alpha times the square root of H. So now, if we begin to think about our reference temperature, we could use anything for our reference temperature. We could use 0, 1, whatever we wanted. So technically, our reference temperature does not have that much of a use in this equation. So we can actually just get rid of all of these. All right, so now our new equation is going to be the area times the change in height times the temperature. And we can see we still have our CV right here, but that is also going to be a constant, so we can pull that out. That's not going to change with time, but the temperature will change. So this is going to be equal to Cp times T times Qn minus Cp times T times alpha times the square root of H. So now we can see, as we were talking about up here, our Cp is equal to our Cv. So we can divide this equation by our Cv, and these are all going to cancel. The Cp's and the Cv is going to cancel. All right, so now our new equation is going to be the height times dt, or times the change in temperature over the change in time, plus the temperature times the change in height over the change in time is equal to the temperature times Qn minus the temperature times alpha times the square root of H, and this is all divided by A. So now we are going to solve this equation for the change in time, or the change in temperature over the change in time. So we are going to get the change in temperature over the change in time is equal to TQN minus T times alpha times the height, or the square root of height, divided by the area. And this is we are going to subtract down the T times the change in height over the change in temperature. And then we are going to divide all of this by the change in height. So now this is our equation for temperature. Alright, so now we are going to look at our equations in Colab. So we are going to start out by importing numpy as NP, so we don't have to write numpy over and over again. And then we are also going to use a function from SciPy, so we are going to do SciPy dot integrate, and then import solve IVP, so that'll solve our initial value problem. We are also going to use something from Plotly, so we're going to do Plotly dot subplots, and then import make underscore subplots. So we're going to hit shift enter for our code knows what we need here. And now we are going to start talking about our initial value or our initial values. So if we look over here at our right side of our screen, we can see that the area is going to be equal to 1, and this is going to be in meters squared. Our initial height is going to be equal to 1 also, and this is just meters. And then our initial temperature is 300 Kelvin, and our temperature going in is 320 Kelvin. And then we have our Q in is equal to 1, and this is going to be meters cubed per second. And our alpha is going to be equal to 0.4. That does not have any units. And then our time end is going to be 100 seconds. Alright, so next we need to define our ODE. So we're going to have ODE, and then we're going to have our temperature or our time, and then we are going to have a variable K. So we are going to set our height and our temperature equal to K. And now we have to put in our equations from what we just solved on the whiteboards. We are going to have DH is equal to Qn minus alpha times height to the 1/2, and that is all going to be divided, we need to go out more parentheses, divided by the area. Alright, so that is our height equation, and now we need to put our dt in, so this will be our temperature. And we are going to have a lot of parentheses here. We'll make sure that that's right in a minute. So we are going to have our temperature in times our Q in. And then we are going to have subtracting T times alpha times the height to the 1/2. And this is all going to be divided by A, or our area. And then also we have to subtract T times dH. And then all of this is going to be divided by the height. So if we can see here, we do have the correct amount of parentheses. And now we are going to return a numpy array of our height compared to our temperature. We're going to hit Shift Enter. And now we are going to solve our initial value problem. So we are going to use that solve underscore IVP from SciPy. And then we are going to have our ODE, comma, from 0 to T end. And then we also have to have another numpy array in here. So we got numpy.array of our initial height and our initial temperature. And then we have to define our method, and that is going to be redo, R-A-D-U. And then we also have to do our dense output, and this is going to be equal to true. And now we just do dot SOL. Alright. So now we are going to plot this, and we are going to have, well, we're going to get ready to plot it. So we are going to have tplot is linearly spaced, and we are going to have it go from 0 to T end, and we are going to have 300 points. And now we have to define our H and T again, and this is going to be equal to our initial value problem within the values of tplot. We're going to hit Shift Enter on that. Oh, don't know how this got here, but this is not solve, that is just .sol. Alright, so now we are good to go. So now we are going to make our plots, and we are going to do fig is equal to make underscore subplots. And then we are going to have our rows equal to 1 and our columns equal to 2. And then we are going to plot our height. So we are going to do fig dot add underscore scatter, and x is equal to t, and then, oh no, x is equal to tplot, and then our y is equal to our height. And then we have to tell this where to go, so it's going to go to row 1 and column 1. So next we are going to plot our temperature. So we're going to do fig.add underscore scatter, and then x is equal to the same thing, so x is equal to tplot, and y is now equal to our temperature. And we are going to tell it where to go, so it's going to go to row 1, and it's going to go to column 2. So these, oh, we forgot a T in here, so it's make subplots. So these are going to pop up here, and I don't like looking at it when it is white. So we are going to come up here, and under here we are going to add PIO dot templates dot default is equal to plotly underscore dark. To do that, we have to actually go back up here, and we have to import plotly as PIO. So we can do the PIO.templates. Alright, so I went back and looked at one of our previous codes, and we actually have to have plotly.io here for it to work. So now if we run all of these again, now our graphs are going to be on a black background. So we can look at these now. So this left-hand one is our height, and then this right-hand one is our temperature. Alright, so now we are going to look at a second example using the same system. So as we can see up here, there are two variables that I did change. So we are going to look at the comparison of height and concentration instead of height and temperature. So we are going to have our initial concentration equaling 0.1 kilograms per meter cubed. And then our concentration in is going to be equal to 1 kilogram per meters cubed. So instead of a different temperature water coming into our system, we have a solute of some kind coming into our system at 1 kilogram per meter squared. And then also our concentration out is going to be equal to the concentration of our system. Since our system is perfectly stirred, the concentration in our system is going to be equal to the concentration that is coming out. So now, if we can see, I left the equation for height that we derived from the last problem. So this would kind of change because our densities would change just a little bit, but since our densities cancel out, it is actually not going to change anything with our actual equation for height. So our equation for the change of height over the change of time. That's not going to change at all with our new conditions. Alright, so now we are going to find our equation for concentration. So this is going to be the change in concentration divided by the change in time. So we are going to start out just the same as we did in the previous two parts, and we are going to start with the change in the mass of our system is equal to the change of the mass in minus the change in the mass out. So the change in the mass of our system is going to be the change of the concentration times the volume. So again, that is the concentration times area times the height. This will be over the change in time. And then the concentration, or the mass coming in, is going to be the concentration in times the flow rate in. And then when we're subtracting, we're going to do the mass that's going out. So as we said earlier, the concentration going out is the same as the concentration of the system. So we are just going to use C, and then we are going to have it times Q out, which is alpha times the square root of the height. So now we are going to do the same thing we did in the temperature part of this, and we are going to pull A out because A is not going to change as the time goes on. A is going to always be constant, and then we are going to divide it onto the other side. So we are going to get the change of concentration and height over the change in time is equal to the concentration in times the flow rate in minus the concentration times alpha times the square root of the height, and this is all going to be divided by the area. Now we are going to do the same thing we did with temperature, and we are going to use the power rule to split up this left-hand side. So we are going to get concentration times the change in height over the change in time, plus the height times the change in concentration over the change in time is equal to concentration in times the flow rate in minus the concentration times alpha times the square root of h. This is all going to be divided by A. So what we're trying to solve for is this change of concentration over change in time. So that is going to be our left-hand side. And then we are going to get, on the right hand, we are going to have the concentration in times the flow rate in minus the concentration times alpha times the square root of h, all divided by A. And we're going to subtract over the concentration times the change in height over the change in time. And then this whole thing is going to be divided by the height. So now this is our equation for finding the change in concentration over the change in time. Alright, so as we just saw, our equation comparing concentration is very similar to our equation that compared temperature. So all we have to do in our code is we are going to create a copy of this, and we are going to rename it. Alright, so all of this here at the top is going to be the same, and all of our initial conditions are the same, other than we are going to have concentration in now, and this is going to be 0.1, and this is now kilograms per meter cubed, and we have to change our temperature in, now it's our concentration in, and this is going to be 1, and this is going to be kilograms per meter cubed also. So if we shift enter, now we have to go through and change all of our T's to C's. So we are going to have, this is now concentration, not temperature, and we've changed this to concentration. So we are going to have Cn times Qn minus the concentration times alpha times height to the 1/2 divided by area, and then subtracting concentration times d height divided by height. So now we are going to return an array of d height and then d concentration, not dt anymore. And now we must, so we want this to be our concentration initial now. And we also have to come down here and we are going to do concentration instead of temperature. Alright, let's go up here and we are going to reset and run all. Alrighty. So now we are going to have this second graph compare time and concentration. So now we can see the graphs of our height versus our time, and then our concentration versus our time. Thank you for watching.